Okay, thanks for the chair's introduction. I'm Zhenlin from Shanghai Jiao University, and it's my pleasure to introduce our work, Chrono, Meticulous Hotness Measurement, and Flexible Page Migration for Memory Theory. So I will share this work by these 4 parts. And firstly, I'd like to go through the background and our motivation. So currently, we are seeing a rapid growth of memory Turing system for the next generation data center memory architecture. So from the OS perspective, the heterogeneous memory devices have different performance characteristics. For example, for the local DRAM, we has tens of nanoseconds latency and hundreds of GBs bandwidth. But for the CXL-based remote memory, we could have several hundreds of latency and less bandwidth. Since then, the OS need to identify hot and cold pages and place them into different tiers to have a ideal performance. So currently, there are 3 existing hotness profiling mechanisms. The first one is the page fault-based mechanisms. It is compatible with the NUMA mechanism, which is widely used in the Linux kernel, but it has coarse-grained frequency measurement, and it always have higher OS level costs. And second one is the reference bit-based mechanism. This kind of mechanism is slow overhead, but it also have coarse-grained frequency measurement, and it always combined with predefined criteria for the page classification. And then the third one is paths-based mechanisms. They are always fine-grained, but it always combined with a lower space resolution, and moreover, it's a process level solution, so it may have some limitation facing with a complex multi-tenant environment. So for the motivation, we asked 2 questions. The first one, why we need fine-grained frequency in the tiered memory system? The answer is quite simple. The hot pages in the slow tier have high access frequency. Here's an example. We use a DRAM and NVM Turing system and conduct various memory-intensive benchmarks. And we collect the average access latency during the benchmark execution. We observe that the average DRAM frequency is larger than the average NVM frequency. So that is decided by the hardware characteristics. But in the NVM, the top 10% hottest part is much frequent. It is hotter than the average DRAM frequency. That is decided by the software access pattern. So in general, we need a really fine-grained frequency measurement to classify the real hot pages in the slow tier. And second question is that why achieving both fine-grained frequency and high space resolution is hard? It's because all the mentioned methods here are counter-based. So every counting event comes with cost, but the information we retrieved is just 1 bit. Here's an example on the paths-based measurement frequency measurement mechanism. So when we use huge page in this system, the counter values are generally large. But when we use base page, there are more pages, and the counter values are relatively smaller. And we can prove that the variance of the counter value is approximately equal to the expectation. So the smaller values are not reliable. So the paths-based methods are not usually used in the base pages. Then we introduced the Chrono. a meticulous and flexible Turing system. Our first and primary insight is that the timer-based hotness metric is better instead of counter, and this is mainly for the hot page selection. And for cold page selection, we also include a proactive eviction mechanism with a thrashing monitor mechanism to provide a higher availability. So, and we also include a automatic tuning method that can decide the parameter at runtime. This is how we build our timer-based metric. We use the so-called captured idle time or site metric to record the timestamp between the timestamp difference between page scan and page faults. So use that timestamp difference, we represent the some kind of a reflection of the frequency. So in fundamentally it's based on the page scan. So we cyclically poisoning range of page through the VMA, and we store the timestamp of these scan events. Then when there are page access events, there will be a page fault caught by the kernel, and we then store the page fault timestamp. By calculating the difference, we got the site list, and compare every site with a global threshold to define to determine if we consider that page as a hot page candidate set. So every page in the hot candidate set will be rescanned in the next event, and the page fault and site generation are the same, and then we compare it with the threshold again. That means we have a 2-round selection here for the hot page candidate. This is more stable than the 1-round mechanism, and it also has a higher efficiency. There's a balance here, and we have some theoretical analysis in the paper. So finally the selected pages will be pushed into a rate limited promotion queue. It's also a asynchronous promotion queue. So and we want to validate our observation that timers provide fine-grained frequency metric with a controllable overhead. Here we give an example. So we manually configure a normal distributed access benchmark, and we collect the the site states at some fixed points, and the results show that the size value are strongly negatively related with the frequency distribution. So and the results are also shown with the deviance standard deviation bars. So we can see that with 2-round selection, the variance is relatively small, and the CITs are precisely collected. So based on the site metrics, we can design a threshold estimation mechanism, as shown here. We collect runtime site and on the different tiers, and compare them in a aggregated table. So if we found that some slow tier pages has hotter sites value than the top tier, we will say that there need a promotion, and vice versa. In practice, we define 2 key parameters to capture this characteristic. The first one is the size threshold, and the second one is rate limit, which define the migration volume. So this is the mechanism how we define that 2 key parameters. So firstly, we randomly pick some pages to be the victims and scan them, just make them unavailable, and so that your page files, and we can state the site values, and the Chrono just sort them, sort all the site values, and generate a heat map. So we then aggregate all the heat map of the process, and generate 2 heat map for different tiers. So then compare them and calculate the overlap size. So we can redefine the threshold and the conversion rate limit. So Chrono also includes the following optimizations as well. First, we include a proactive demotion mechanism. So we use an extended watermark to reclaim the pages ahead before it is exhausted, and we design a thrashing monitor mechanism that collect thrashing events and adjust the migration rate limit. So, and then we our demotion mechanism is also lightweight and compatible with some limitation, like some mechanism like C group in the mix. And for different page size, we also include the huge page support, which is adaptive, facing various page sizes, and it produces fire-side thresholds for different page size. You can check more details in our paper. And for evaluation, we use a Intel Xeon Gold CPU with 64 GB DRAM and 256 GB NVM to build the memory tuner system, and we use a bunch of memory-intensive workloads here. So with TMap bench, we measure the average latency, medium, and P99 latency. It shows that Chrono reduced the latency values compared to the existing solutions, and we also collect the runtime kernel level statistics, which include the kernel time, that is the kernel level overhead, and also the context switch rate, which shows that the Chrono has a slightly higher context switch rate compared to the hardware-based methods, but it do reduce the switch rate compared to the Linux kernel. And we also validate our parameter tuning scheme, which is called DCSC, and by logging the key parameters history during execution, and compare them with the ideal target value, and it shows that Chrono perform more intensive migration at the start of the workload, but it will be more stable after a long-term execution. I also do the sensitivity analysis in the right graph, which show that Chrono can be adaptive for different parameter settings. I will also do some macro benchmarks on the database and the graph applications. So it shows that Chrono generally improves the throughput for different applications, and it also is adaptive to different page size. Well, a whole page can improve the throughput in different scenarios. Chrono can improve the overall performance compared to the original Linux kernel. And then we also analyze the different design part of Chrono, which include the timer-based metric and the two-run selection process. Also, we evaluate what if we have more run selection, and we also evaluate the auto-tuning methods. It shows that timer-based metric is fine-grained and lightweight, and our two-round selection is reliable and is efficient compared to more round. And our tuning method definitely give a better estimation on the parameter, so it increases the performance. So as conclusion, contour-based hotness profiling is not fine-grained. So Chrono is meticulous and flexible tuning system, as it's using timers to record the page idle time, which reflects the frequency, and it uses automatic adjustment on the collapsing criteria, and it's compatible with the length page reclaiming, and it also reduces the thrashing phenomenon. So results show that Chrono outperforms existing hot code page identification methods. It has higher overall performance with less configuration efforts. So that's all. Thanks, and free to ask questions.